Hello. In this uh, in this video, I'm going to take you through a lab work, that is estimation of calcium with ethylene diamine tetraacetic acid, which is EDTA. The ethylene diamine tetraacetic acid is also called EDTA. That is a short form for this ligand. Um, and I will take you through um, the aim of this experiment. Introduction. The introduction will contain the method that we will use in this experiment, and I'll explain complexing agents and chelating agents, and I'll also talk about the principle behind this experiment, and I'll take you through the procedures and why some actions are taken in the procedures, calculations, and I'll give you a pre-lab guide, so that, and work, I also have a work example for you to enhance your understanding on this lab work. So I see, I'll make everything easy at the end of this video. So please, let's start. So the aim of this experiment is to estimate calcium ion concentration with EDTA. We are using EDTA to estimate the concentration of calcium ion in a given solution. And the method that we are using in this experiment is complexometric or chilatometric titration. Complexometric or chilatometric titration. And what is this? You have to understand this. This is how do you call it? A titration form. I mean, it's a form of volumetric analysis that determines the concentration of metal ions by reacting them with a complexing agent. And here comes a complexing agent. And I also have to explain complexing agent to you and a chelating agent to you, so that we will get a better understanding of the lab. And the complexing agent that is mostly used, I mean, that is typically used in this lab is EDTA, that is ethylene diaminetetraacetic acid. So now, a chelating agent is also, I mean, a complexing agent. What do I mean by this? Complexing chelating agent is a specific type of complexing agent that form, I mean, a ring-like structure with a metal ion. And this one as a chelating agent, I mean, it forms a very stable complex. That's why a specific name is given to it as a chelating agent. Example of that ligand is EDTA. So a complex formed by EDTA mostly is very stable as compared to some of the complexing agents. For instance, Na3 is a complexing agent, H2O is a complexing agent, EDTA itself is a complexing agent. But there are some of the complexing agents that are given specific name as chelating agents. So the reason why we give them specific name is that because they form a very stable complex as compared to others. That's why they are given specific name as chelating agents. So now, chelating agent is okay, complexing agent is okay. Now we can now look at the principle behind it. Let's look at the principle behind this lab. EDTA is a chelating agent or scavenging agent. This ligand, when it, I mean, in a solution, when there's a metal ion in a solution and you add EDTA to that solution, there's a high chance that, EDTA is going to form a complex with a metal ion. So this experiment, a simple application of this experiment is that it's mostly used to, I mean, like I already explained the method complexometry. We use a ligand to determine the concentration of a metal ion in a solution. So EDTA is a complexing, I mean, it's a chelating agent. So the reason why we are using EDTA is that EDTA form very stable complex with metal ion, provided those metal ions are present in the solution. So if we have calcium ion in the solution and we add EDTA to it, there's a high chance that there's a high probability that EDTA is going to form a complex with Ca2 plus, which is very stable, Mg2 plus. So this particle is usually applied to determine whether the hardness of water, because we know that calcium Ca2 plus and Mg2 plus are the various, are the things that causes hardness of water. So it's applied to determine the concentration of calcium ion and magnesium ion in a given solution. In this experiment, mostly the concentration of EDTA is known. We know the concentration of EDTA, and we take a known volume of the solution that contains the Ca2 plus, and we titrate it against EDTA, the average volume, the titer or the average volume of EDTA that's going to react with the solution to give us an endpoint. We therefore balance our overall equation and calculate for the concentration of Ca2 plus. So it's possible. I don't want to dive into it now. Let's go to the procedure so that you get to understand more. So now procedure. First of all, we form a standard solution that contains calcium ion. First of all, standard solution that contains calcium carbonate. But one thing you have to do is that just listen to your demonstrator for this lab and or your TA for this lab, and you'll be fine. I'm just trying to enlighten you on the topic so that before you start these practicals, you get a better understanding of it. And if you have any problem to or any suggestion to, you can also let me hear in the comment section. And don't forget to support me by subscribing and sharing for me to be able to do more content like this to you if you found this content very helpful. So we form a standard solution of CaCO3 in a volumetric flux. Let's say if we are to use 250 volumetric flux, we measure a given calcium carbonate, we dissolve it in water. And we also add HCl to it. Why are we adding HCl to it? Because, mind you, this is a process of forming our standard solution. So we dissolve our calcium carbonate in water, and then in water, and we add HCl to it. Calcium carbonate normally is not all that soluble in water, so we have to add HCl to aid in dissolution. So if you check this mixture very well, you will see that there is going to be an effervescence in your, in your mixture. You are going to see effervescence in the mixture that you form. And what causes that? You see, our HCl plus our calcium carbonate is going to give us calcium chloride plus water plus carbon dioxide. And this carbon dioxide is what is causing the effervescence in the solution. Mind you, this is our first step of the procedure. We form a standard solution of a substance that contains the Ca2 plus ion. This 250 stands for the volumetric flux that I'm using for this practicals. So you might use different volumetric flux. That will depend on your demonstrator. So secondly, after we form our standard solution, we take 10 ml of our standard solution plus 20 ml of distilled water. Water plus 2 ml of buffer solution plus 5 to 6 drops of our indicator. Here the indicator that we are using is Erichrome black tea. Black tea. So let's take this, let's break this very well. We take 10 ml of standard solution that contains Ca2 plus ion, 20 ml of distilled water, and 2 ml of buffer solution. So why are we adding buffer solution to the mixture? Why? Because we are adding buffer solution in order to maintain the pH range of 8 to 10. Why? With a pH range of 8 to 10, we are going to get the more deprotonated form of EDTA. Let's say if we represent our EDTA with Y, the fully, deprotonated form of EDTA is Y minus 4. So at a pH range of 8 to 10, this form of EDTA is available to form a very stable complex. The higher more deprotonated form of EDTA, the more ability for it to form a complex with a metal ion. So that's why we are maintaining a pH range of 8 to 10. And one other factor that can also help us to maintain, to get a highly deprotonated form of EDTA is also temperature. High temperature gives us this, and low temperature also gives us the other. This is our, let's see what is happening here. So after we added our buffer solution, then we add our indicator in 5 to 6 drops. And what is going to happen? Let's see our color change. Erythrochrome black tea, a solution of EBT is generally blue. And when we add our EBT, erythrochrome black tea, into the solution sample, the solution is going to turn red or wine red. Why? Because the indicator is firstly going to form a complex EBT C2 plus complex. Is going to form a complex with the metal ion. That is why the color of the indicator solution changes from blue to wine red. So, and this is also a clear indication that yes, there is a presence of Ca2 plus ion in the solution. Because after we added our indicator, just see the color will just change to wine red. So after we added our indicator, the second thing, what follows is that we are going to titrate it against our EDTA. We are going to fill our burette with EDTA and titrate it. If we add our EDTA gradually, if we add our EDTA onto the solution in the conical flask, if you add our EDTA to the solution in the conical flask, if we get to the end point, the color is going to change from wine red to blue again. So blue to red, let me call it red to blue. So a color change from red to blue tells us that the EDTA has now formed a very stable complex with the metal ions in the solution. Why is this happening? The EBT, the erythrochrome black tea, will form firstly form a complex with the metal ion. But this complex is not more stable. It's not very stable. So when EDTA comes into the solution, it's going to displace the indicator and takes charge of the metal ion. So EDTA is the one that is going to form the more stable complex with the metal ion, which will be indicated by a color change from wine to blue again. From wine red to blue again. This is the structure of erythrochrome black tea. So this one will form a complex with the metal ion first, which will which will show a color change of wine red. And this one, EDTA, because it's formed a very stable complex, will come and displace that indicator. So EDTA, this is how EDTA forms its complex. That's how we call it chelating agent. See how it surrounds the central metal atom. So definitely this complex is going to be very stable. This is a normal structure of EDTA, and when EDTA form a complex with a metal, this is how it looks like. So if you are asked why color changes, you should know that EDTA, a solution of EBT is normally blue. So when you add it to the solution in the conical flask, it's going to give us a wine red EBT metal complex. And when you add EDTA to it, after EDTA form the most stable complex, the color will change from wine red to blue again. EDTA. a metal complex. So this is what you should know here. So we are done with the procedures. Let's look at the calculation aspect. The calculation aspect of the experiment. Assuming after our titration, we got our average titer to be 11.9 ml. So this average titer is the volume of EDTA that reacted with the metal ion to form the complex. So this is the volume of EDTA. V EDTA equal 11.9 ml. Let's convert it to DM. Keep straightforward. So you get 0.0119 DM cube. So we know the concentration of our EDTA already. The EDTA will definitely know its concentration. So C EDTA. Let's say our EDTA that we use has a concentration of 0.1 mole per DM cube. So now we are going to calculate for the mole of our EDTA. What's the mole of our EDTA? So we know that we are going to use this general formula. C equal N out of V. And we know that N equal C by V. So this is the formula we are going to use. So our mole of EDTA equal concentration of EDTA multiplied volume of EDTA. And we know the concentration of our EDTA to be 0.1 mole per DM cube multiplied by 0.0119 DM cube. If you point this on your calculator, you are going to get 1.19 by 10 raised to the power minus 3 mole. First, we know the concentration of our EDTA and our average data is the volume of EDTA that reacted with the solution in the conical flask. And we now calculate the mole of, the mole of EDTA. Now that we know the moles of EDTA, we can now calculate for, the moles of Ca2 plus by, looking at the stoichiometric ratio. EDTA, the ratio of EDTA and Ca2 plus is 1:1, definitely. That is why we are much interested in using EDTA. It reacts with the metal ion with the ratio of 1:1, and nothing is going to change that. So now, since we got a ratio of 1:1, that means mole of Ca2 plus is the same as this. Going to give us 1.19 10 minus 3 moles. I hope you are getting me. Now that we use this procedure, calculated for the moles of EDTA, and now we look at stoichiometric ratio. You know that since the ratio is 1:1, we get Ca2 plus moles of Ca2 plus to be 1.19 like this. What's the next thing we have to do? We are now going to calculate for the concentration of Ca2 plus. So let's do that. For the concentration of Ca2 plus, now we know the moles of Ca2 plus, which is 1.19 10 minus 3 moles. And what is the volume of our Ca2 plus? From the procedure, we took 10 ml. We took 10 ml of our prepared solution plus 20 ml of distilled water. So the total volume is going to be 30 ml. I hope you got that, because we took 10 ml of our prepared sample and 20 ml of distilled water. So if we convert this to DM cube, what are we going to get? We get 0.03 DM cube. So we want to calculate for concentration of Ca2 plus. And what's the relation? C equal N over V. So definitely we know our N, and then we also know our V. So we can therefore go straight forward to, so we're going to, our N is 1.19 by 10 minus 3 mole all out of 0.03 dm3. So we are going to get concentration of CH2 plus to be 0.0397 mole per dm cube. So now that we are done with calculating the concentration of CH2 plus, what next can we do? Mind you, we took 10 ml of a prepared sample that contains the Ca2 plus. And we also added 20 ml of distilled water. Now we have to calculate for the concentration of Ca2 plus in the 10 ml of the sample that we took. So equivalent concentration of Ca2 plus in 10 ml. Let me do this so that we get. So we are going to calculate for equivalent concentration of Ca2 plus in the 10 ml of the solution that we took. So, and the formula that we are going to use here is C1V1, C2, V2. So, assuming concentration of Ca2 plus ion in the 10 ml is C1 and volume of Ca2 plus in the 10 ml is V1. Of 2 plus in 10 ml. For this one, we don't know, but for V, we know V1. For V1, we know it because the volume of the solution, the volume of the prepared solution that we took was 10 ml. So this is the volume of the solution that contains the Ca2 plus ion. So that means we get 10 ml. So if we convert this to dm cube, we are going to get 0.01 dm cube. So 0.01 dm cube. And so we now define C1V1, C2V2. We define our C1V1, C1 concentration of Ca2 plus in the 10 ml solution, and V1, the volume of the solution that contains the Ca2 plus, which is 10. And the next thing we have to do is to define our C2 and then V2. Our C2 is the concentration of Ca2 plus in the whole mixture, the 30 ml, where we took the 10 ml of the prepared sample and 20 ml of water. So that concentration, we calculated it to be 0.0397 mole per dm, which is here. So now we know our C2, and our V22 is the volume of the total solution that we made, which is 30 ml, 10 ml of a prepared sample and 20 ml of distilled water. And converting that to dm cube, we get 0.03 dm cube. So now our C1V1 equals C2V2. What we are looking for now is our C1, because that's the concentration of Ca2 plus in the 10 ml of solution, in the 10 ml solution. So now if we make our C1 the subject, we are going to get C2V2 all out of V1. So let's substitute the values into the equation. We know our C2 to be 0.0, our C2 is here, 0.0397 mole per dm cube, and our V2 to be 0.03 dm cube, 0.03 dm cube, this is 3, divided by our V1. Our V1 here was the volume of the prepared sample that we took, which is 10 ml or 0.01 dm cube, 0.01 dm cube. So if you point this one on your calculator, you are going to get 0.100 mole per dm cube. So this is the concentration of Ca2 plus in the 10 ml solution that we took. So your demonstrator or your TA might also add some concept to it. So the best thing is you have to listen to your demonstrator very well, and then this is just to help you out to get a better understanding. I mean, a good understanding about the topic, or should I say, a better understanding about the topic. So now let me take you through. Let me guide you. Let me give you the pre-lab guide. For the pre-lab, I don't want to make the video all that length. So you have to know what ligands are. You should be able to define what a ligand is, and then coordination chemistry. I mean coordination compound, coordination compound. And probably you should know some naming, how to name some of the coordination complex. It is very bad. We're going to manage. And you should know what coordination sphere is. Coordination sphere. The coordination sphere is just simple, the metal atom together with its surrounding ligands. And you know what a ligand is, any atom or ion that is directly bonded to a central metal atom. In coordination compound, you should be able to define that. And what chelating agent is. Chelating agent, complexing agent, like I even explained this at the beginning of the video. Complexing agent. And EDTA. EDTA is a hexadentate ligand. Hexadentate because it forms, I mean, identity, it has a density of 6. Number of donor atoms a ligand has to I mean, EDTA has 6 donor atoms. So that is why it is called hexadentate ligand. So EDTA is hexadentate, total number of 6 donor atoms. And if you should know the structure of EDTA, I think it will also help you for your lab. And this is the structure of EDTA. So I think that's you should be also familiar with this formula C1 V1, C2 V2, or concentration formulas. You should be familiar with this. And the last thing I want to do is a work example, how this is applied. A 50 ml sample of hard water is titrated with 0.01 molar EDTA solution. The volume of EDTA solution used to reach the endpoint is 25.0 ml. Calculate the mass of calcium ion, I mean Ca2 plus, in the water sample. So 50 ml sample of hard water is titrated with EDTA. 50 ml titrated with EDTA. The volume of EDTA solution reached endpoint. The volume of EDTA that reacted with the sample to give us an endpoint was 25.0 ml, and the concentration of EDTA 0.01. So we are to calculate the mass of calcium ion in the water solution. So this is what we can do. Let me make everything simple. So calcium, I mean Ca2 plus EDTA form a complex in this form. Ratio is 1:1. We don't know the moles of our EDTA, but we know the concentration of EDTA, and we also know the volume of EDTA. That is the titer value, the average titer, which is 25. And what we can do is to calculate for the mole of EDTA, because if we know the moles of EDTA, the moles of EDTA is going to be the same as the moles of Ca2 plus. I need to say more. Pardon me for that. So we calculated the moles of EDTA to be 0.0025 moles. So that is definitely going to be the moles of Ca2 plus, because the ratio is 1:1. So now the molar mass of Ca2 plus calcium is 40.08 gram per mole. And we now know the moles of Ca2 plus, which is this. And now we know mass is also related to molar mass and then moles of a given sample. So molar mass by moles gives us 0.01 gram. So the question now is answered that we should calculate the mass of calcium ion in the water sample. So this is the solution. So hope you found this video helpful. You can support me to make more content like this. Better content by subscribing to my channel and also like my video. You can also share and give a comment. If you have anything bothering you, suggestion or anything, you can let me hear you in the comment section. Thank you for watching.